Hello world, this is Craig. I wanted to learn more about this programmer on this MIL mod system, and first it was out of necessity because mine wasn't working as soon as I got it built a couple of days ago, and I wanted to find out why, and so I had to dig into this and learn a bit more. So for future me, and maybe anybody else that's interested, I wanted to document that so I know exactly what's going on with this thing in case I ever have to diagnose it again. First thing we need to do is look at what's required to program the 1702, or the 1702A in this case. So this is the programming waveform for the 1702A, and the first thing we have to do is set up the complement of the address to be programmed. And it's not just the complement that's the problem, it's actually we have to then have voltage rails that are between 0 and minus 48 volts. A logic true is 0 and a logic false is minus 48 volts. After the required 25 microsecond setup time, we then take VDD and VGG to their programming levels, and in this case it's minus 48 volts and minus 35 to minus 40 volts respectively. They're at their programming levels, and now we take the data to its value, and for the 1702A the data has to be complemented before it's presented to the chip, and it has a little bit of setup time, and once its setup time has gone past, we can flip the address from the complemented value to its normal value, and then we give it the programming pulse, and the programming pulse has to be 3 milliseconds to prevent this thing from overheating. That's the maximum programming pulse. After the programming pulse is released, we have a little bit of a hold time for the data, and for the VDD and VGG, then that can all be released. Then we have a little bit of a hold time for the address, which can be released, and we're done with the programming cycle. Now, for these chips, it takes a lot of programming cycles in order to get this to stick. And as a little bit of a side, we can understand that. We can understand why we have to hit this thing so many times and why we have to hit this with such large voltage. Because if we think of what we're doing, we basically have a transistor. So this is our transistor, and we don't have a gate directly connected to this. So we can't, there's a little area here in the semiconductor that we're influencing the number of conduction electrons in this. And so we either push electrons in this so that this can conduct from the source to the drain, or we get rid of those electrons so this can't conduct. And we normally do that by having a gate out here. We have a gate out here that will push electrons into this area or carriers into this area, or deplete this little area from the carriers. And so in this case, we'll call this our select gate, because that's going to select this chip whether to turn it on or off. Now, for the EPROM, we have another area in here that is not connected to anything. So this is a floating gate. What happens is, if we want to program this, we have to push electrons onto this, because normally this select gate can't turn this transistor off and on by itself. It just doesn't have enough influence on this, particularly since there's a large area and there's this little floating gate between them. So what we want to do is we want to bias this area, and the way we bias this area is by pushing charge onto this little floating area. But this little floating area isn't connected to anything, and so we're basically relying on leaking and tunneling to get electrons into that area. So we want electrons to go into that. The way we do that is by applying large voltages. So we apply minus 48 volts on this, and we just keep hitting it, bang, 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 over and over again. We hit it 30 times, and then we'll go back and we'll check it, and we'll see if that has made it so that this has remembered its address. And if it has, then a typical programming is to say we're going to program 4 times more than it took to get this gate to switch over. So if it took us 30 times before we first saw this gate switch to a reliable value, we're now going to give it another 120 pulses in order to get enough electrons into that thing so that long-term this thing is stable. And of course, to get these back out, we expose this to UV light, and then these electrons are able to tunnel back out with that once they get the energy of the UV light in there. So that's the goal. That's what we're trying to do to this thing. And because it's not a simple task to get these electrons to tunnel in there, because after all, this is very isolated. If it weren't isolated, eventually they would leak back off again, and we would lose our memory. So it's not easy to get these things on, simply because it can't be easy to get these things to come back off again. So that's what we're trying to do. That's why it takes such a large voltage to get these on, and that's why it can take hundreds, if not 1,000 pulses of that voltage to get the electrons, enough of them to trickle into that isolated gate so that this thing remembers what logic it's at. Okay, so that's what we have to do. Now let's look at what we're going to do to make our life a little bit simpler. Well, a couple of things we can do to make our life simpler, and that is that we can put the address and the data onto this chip as early as we want. So we're going to put the address on, we're going to put the data, present the data to this chip, and we're going to let the microprocessor do that a long time ahead of time so it doesn't take a bunch of, because the timing is not critical. And then right when we start our programming, we're going to complement that address, and then we're going to actually bus that data, present it to the chip with a hardware gate. So that's the first thing that we can do to simplify our life, is to not worry about the critical timing, or not worry about the timing because it's not critical, of exactly when we put the address and the data onto the bus. Now let's summarize what we require to program this chip. And so we're going to make a table here of what our signal is, or our bus, our power supply is, and we're going to say when we are reading this chip, or when we are programming this chip, and when we're actually giving it the programming strobe. Okay, so first let's look at VCC. When we're reading this chip, VCC is at 5 volts. And then when we're programming it, we take VCC to 0 volts, and it stays 0 volts during the programming strobe. So it's 0 volts for both of those. VBB is normally 5 volts when we're reading the chip. When we want to program it, it's the same thing. It's going to be at VCC plus 12 volts in both cases. VDD is normally at minus 9 volts when we're reading it. When we're getting ready to program it, we take it to VCC, and then when we're actually strobing it, we go to VCC minus 48 volts. And so that's what we see back on our waveform, where we took that down to between minus 46 to minus 48 volts. VGG, same kind of thing, minus 9 volts when we're reading it. We're getting ready to program it, we take it to VCC, which is 0 volts, but when we're actually strobing it, we take it to VCC minus 36 volts. So unfortunately, not quite the same. Our programming pulse, when we're reading the chip, that's 5 volts. When we're programming it, we take it to VCC. And then when we actually pulse it, we go to VCC minus 48 volts. Our chip select is normally at 0 volts when we want to read it. And then when we're programming it, we take it to VCC. And that's the same as when we're applying. It is not strobed. It's always at VCC. Our address, 0 to 7. Normally, when we're reading the chip, and so we want to give it an address, those are 0 to 5. And then when we're actually programming it, we'll take those. They'll be between VCC and VCC minus 48. And the same as our data, 0 to 7. Normally this is a 0 or 5 volt output. When we're programming, these will go from VCC to VCC minus 48. All of these negative voltages are a problem. They're tough to interface. What they did in this, and what everybody else was doing at the time, including Intel when they put out their spec sheet, they translate this. If you look at the chip, it's interesting. There's 2 pins for VCC, but there's no ground. So ground itself is not defined on this. So we're going to take VCC and up this by 48 volts. Okay, so we're going to actually connect VCC to 48 volts. So what that does is during our 2 programs, so our program getting ready and our program when we're strobing that pin, our VCC is now going to go up to 48 volts. And that's going to be a steady 48 volts the whole time. VBB, which we've defined as being VCC plus 12, so that's not going to go up to 60 volts. And that's going to be stable. It's going to be the same on no matter what we're doing to the chip. VDD, we said, is going to either be at VCC, which is now 48 volts, or when we're programming, it's going to be VCC minus 48 volts, so its programming strobe is going to go down to 0 volts, down to ground. VGG either went from VCC, which is 48 volts, or it's going to go to VCC minus 36 volts, which is down to 12 volts. Our programming pulse goes VCC, which is 48, or VCC minus 48, which is 0 volts. Our chip select is just at VCC, which is 48 volts. And our address now is going to go between VCC and VCC minus 48. So either 48 or 0, and the same as our data, 48 to 0. And of course, here the data was an output. Now when we're programming it, this data is an input. So this is what we've done. We've taken it so now we have no more negative voltages. We're writing this entire chip up on top of 48 volts. We have the 12 volts above the 48 volts to get our 60, or we have our 36 volts below the 48 volts to get our 12, and then otherwise we're just flipping between our full 48 volts and our ground. So this has made the interface much, much simpler. Now let's look at the circuit on the MOD8, which is the backplane, to accomplish this. And again, what they wanted to do was minimize the amount of time that the microprocessor had to be playing with this programming. They wanted to automate the entire programming sequence as much as possible. What the program does is first it's going to output the address and it's going to output the data to the chip. And it's going to complement the data before it outputs it, because this chip requires the complemented data for the 1702A. Then it's going to start one of these two multivibrators, and it does that by either making data bit 1 or data bit 2 true, so one or the other, and then it writes that value out to port 13, and in doing so that starts one of these multivibrators going. Now one of these is going to operate and provide us a 15 millisecond pulse, and the others is going to provide us a 150 millisecond pulse. Now during that 15 millisecond or the 150 millisecond, the first portion of that is going to be our actual programming sequence that we looked at for the waveform, and then it is just resting the whole rest of that either 15 or 150 milliseconds, because that gives us the required duty cycle for this. We can't constantly hit this chip or we'll get it too hot. We have to hit it and then we have to wait a long time. That's what they mean by saying they can either be the 2% or the 20% duty cycle. We hit it and then we wait. We either wait essentially 150 milliseconds or we wait the 15 milliseconds, and then we hit it again and then we wait. We hit it again and we wait. So these two multivibrators, we turn one or the other on at a time, and that defines how often we're going to hit these things, and that defines our duty cycle. Now when either of those triggers, the output of this gate then trips this multivibrator in 15A, so chip 15 multivibrator A. It goes off and it's going to define a 3 1/4 millisecond pulse. That output in that 3 1/4 millisecond pulse does a couple of things. The first thing it does, it triggers another multivibrator that's going to give us a 60 microsecond pulse. What that multivibrator does is it complements the address. So that's where our complemented address comes from. And we'll look at a little lower in the circuit here of how we complement that address. But basically, that first multivibrator, the 15A, has created the programming voltage enable signal. And so that's when we're doing all of our programming during that programming voltage enable. And this whole PVE is only, this 3 1/4 milliseconds long within this either 15 millisecond or 150 millisecond stream. So when this PVE goes true, it enables all of our programming voltages. And so we can see here on the diagram how those are getting enabled. When this PVE comes out of this multivibrator, this Q bar turns on T5. And when T5 turns on, that's what brings this entire chip up by the 48 volts. You can see how it does that. There's a 43 volt Zener here that's referenced to ground. And then on top of that's a 7805, so a 5 volt regulator. And so that defines CS and VCC down here as 48 volts. So that that satisfies that need for VCC to be at 48 volts, because that brings the entire chip up, as well as CS along with it, the chip select. Now D2 sets VBB at whatever VCC is plus 12 volts because of it's a 12 volt Zener. So VBB is now at 60 volts. D5 sets VGG at VCC minus the 36 volts it requires. So that's the setup for all the programming pins except for the actual programming strobe. That's taken care of by these two multivibrators down here. So this first multivibrator gives us the setup delay required between when we first put the address up and when we drop these voltages to their programming level. There's a setup time required before we can actually strobe the programming signal. So that's what this first delay does. This first multivibrator, it gives us that delay. Then the second multivibrator gives us an actual 3 millisecond programming strobe. And so it does that by disabling T7, and then this 10K pulls the program pin down to ground, which is its programming level. Then when we're done with that, we turn T7 back on again, and then program pin is pulled back up to the 48 volts. The PVE expires, and when PVE expires, that allows us to take all the voltages off the bus. It allows us allows the data to come back off the bus. So this sequence is automated. So again, the intent was that the microprocessor would set up the address, it would set up the data, and then it would enable the programming multivibrator, which is what triggers this entire programming sequence. And it would continue to hit this chip until we went back and turned that multivibrator back off again. So if we knew that this was going to take 150 milliseconds for the entire programming sequence in that multivibrator, and so if we left this enabled for 1.5 seconds, we knew that we would get 10 programming pulses done. We could then go back in, do a read to see if it took that value. If it didn't take that value, we could give it another 10 by waiting another 1.5 seconds. And if it did take that value, then we would decide, well, are we going to give it the 4 times over programming? Here are the actual waveforms on this using my confidence test. And in my confidence test, I can actually turn off either of the multivibrators individually, and I can set the data to either 0 to 1 so I can watch, so I can do some diagnostics on the programmer. Here you can see that I have the slower 150 millisecond multivibrator turned on for about 4.5 seconds, and then I turn on the faster multivibrator for a few seconds here in the second part of the input 5. This is the actual latch that turns the multivibrator on, and we can see the multivibrator re-triggering in the 2 traces below that, and each of these re-triggers are the 150 milliseconds. So let's go ahead and zoom in on this. The top trace is the 4.6 seconds that the multivibrator was turned on. So that's the entire time that this was on. This is the in this case, 160 millisecond pulse that the multivibrator puts out before it re-triggers itself. We can see from the circuit that Q bar output comes in, and there's a little 200 puff capacitor here that re-triggers the multivibrator going back to this gate. And interesting enough, if we look at this trace, which is 13B pin 5, that's the input down here, and we can see that that is remaining low, meaning that the logic analyzer was not picking that up as changing. And the reason is, let's look at that circuit a bit. That's just it's AC coupled with that 200 puff capacitor, a 220 ohm pull down. So I turned on the voltage to actually look at that in terms of voltage, and we can see that that is just riding right here at 0 volts. And then when that re-triggers, when that Q bar goes low, it sends out a very small pulse that just comes up to 1.25 volts, whatever, and it is just enough to re-trigger that multivibrator. So it's not showing up on this trace, but it is actually showing up as a very fast pulse and very low pulse that comes through there to re-trigger that vibrator. So this took me a while to find because I had this logic analyzer on it and I wasn't seeing a pulse there. And I thought, well, that's my problem. I got a bad gate. But actually, when I investigated a little bit further, I could see, yeah, I am getting a pulse there, but it's just very small and it's capacitively coupled. So in fact, even putting a scope probe on it, I influenced that enough that I could get that to go away and stop re-triggering. So let's zoom in a little bit more. And at this point, we can see on this trace our it's supposed to be 3 1/4, but this is actually closer to 4 millisecond. And this is our program voltage enable signal. So this is the entire programming pulse. So again, this is just a little small part of the entire programming sequence that's defined by that first multivibrator. So this is our 3 1/4, in this case 4 millisecond pulse, and that's further defined by some smaller pulses. This strobe is our 70 microsecond address complement. This 14B Q bar output is our delay so that we have our address set up and our voltage and our PVE voltages set up. So this is all of our setup time. And finally, that triggers our programming pulse, which is this 3 millisecond signal down here at the bottom. So that's all of our setup. You can see where we complemented our address, and then we released our address back to the true value. And right here we start our programming pulse, and we get our 3 millisecond programming pulse out of it. Then our PVE falls, which takes our voltages back to their normal read level. And then we wait and wait and wait. We wait the full, in this case, the 150 milliseconds until we do the whole thing over again. Okay, so this is the 150 millisecond delay. This is the shorter duty cycle programming. We can flip over and look at the fast programming, and it's exactly the same thing. In the fast programming, this is the enable for that multivibrator. That multivibrator fires up, and we see the exact same programming sequence, except now they happen every 15 milliseconds instead of every 150 milliseconds. We can zoom in on one of those. This is our 4 millisecond PVE signal. This is our 67 microsecond address complement signal. This is our setup time for the address and all of our voltages to settle before we hit it with the programming strobe. And here's our 3 millisecond programming strobe. And the timing on these is exactly the same because they're the exact same timers. That's what the waveforms look like. Now let's look at some of the waveforms on the scope. These are the higher voltage ones, so I only used the logic analyzer for the lower voltages. So first of all, here's the address when it's false. So when the address is false, this is where we have to complement it. So this is that short period of time that we complement the address, and it goes up to the 48 volts and then back down to 0 volts. So this is a address false signal where it's complemented, making it true, and then it goes back to the true address. Okay, so that's an address false signal. Here's an address true signal. So the address true signal, we can see here where it complements it. So this is our complemented period, and then this is our programming pulse period. So that's an address true signal. Here's our actually complementing signal. So in this case, the red line is the VCC pulse, and so this is when we're doing a read. It jumps up to the 48 volts. And this is our little short, this blue line is our little short address complement signal. Oh, and I forgot to mention, how do we complement that address? Well, to complement that address easily, we just run it through a exclusive OR, the 7486. And the exclusive OR will either let the address go through uncomplemented, or it'll just complement it when we take the address complement signal low. So that's the easy way that we complement that signal. This is actually our program signal and our PVE signal. So the program is in the red. So we can see that this is our programming pulse. It's normally at 5 volts during a read mode. Goes up to 48 volts when we're not strobing the program. So that's during the complement period part of the address. And then when we are giving it the program strobe, that drops back down to 0 for the duration of that strobe, which is the 3 milliseconds. then it goes back up to the 48 volts. And when we're done with the whole programming cycle, that drops back down to 5 volts for the read. This is an interesting one. This is the VCC signal, shown in red, and the address complement. So if we look at our schematic, the voltage program enable triggers both of these. It's the one that puts all of the higher voltages onto the VCC so that it floats the whole chip up. And at the same time, it outputs the complement for the address. As we can see, there's at most a 500 nanosecond delay between those. So the address complement comes down, so it's going to complement the address. Essentially, at the same time, it's putting the voltage onto the chip and floating the chip up. And this is interesting because the setup time after the address complement is put onto the bus and before the voltages are taken down for the programming, to get ready for the programming, on the original 1702, the programming, the setup time was like 1 microsecond, but then that didn't require a complemented address. For the 1702A, requires the complemented address, and the setup time for that complemented address is 25 microseconds. So it's interesting that they are triggering both of these the same, and they're not giving it that 25 microsecond setup time. So it's interesting that it still seems to be working, but they actually should have put in another delay in this so that the VPE first complements the address and then has a slight delay before it starts dragging the chip up to the 48 volts with the VCC. So it's interesting in this case that they're not actually meeting that setup time, but it still seems to be working. And I looked at that a few different ways and getting basically the same result every time, with a chip or without a chip, and there's not that much of an additional load. Since they do have this little current limiter here on T5, I was thinking that maybe that would slow it down enough, but it doesn't. This pops right up, and they're not meeting that setup time. Well, that's all I have for now. I wanted to understand this programmer, and I think I have a pretty good handle on that now, how it's working and what the waveforms should look like, and I've saved these so that later if I am having trouble with this again, I can find my way through it quick enough. So in the next video, I think I'll show you actually what the problem was when I first built this system. I basically had a bad chip, and I can show you where that was, and some other interesting things that I found out when I've been porting the monitors over. So that's it for this video. I hope you enjoyed it and got something out of it, and thanks for watching. Bye.